Having severe vision loss in correcting and good vision, and then the child might have a cataract for a year or maybe even for half a year, and it's corrected by the optics of the eye are corrected by the camera warps, and the brain can't see. So what's the difference? Hummel and Wiesel did an experiment where they checked the connections between the eye and the brain, and that was shown in the right hand side. The open eye, the white eye's connections were taking over way more than their fair share of cortical circuitry for vision. And the closed eye had those little piddly, black holes, and this was an amazing demonstration, a very important demonstration, in fact, of the use it or lose it concept in the brain. That the brain connections require usage in order to be maintained the faculty of the usage form. And if you're going into what you're building on the network and having video forces of the brain do this in real time, this really illustrates the developmental critical periods that happen after birth. We actually are quite interested in the earlier developments of the critical periods in the visual system, and what we discover on and on, that even before babies are born, the eye is sending signals to the brain to start to really shape up these beautiful stripes and these connections in the central pathways. And the signals are the electrical signals that are being sent from the neurons in the retina into the central parts of the brain. And they're actually like test patterns. They're testing the connections, and the ones that are appropriate are being maintained and the other ones are being pruned away. So this is the same theme. And on the video that you see now, there's a picture of this signaling process in the eye. And you can imagine it's like phone calls being placed in the brain really early on in development. And every little black dot in this is about the size of so you can see a pea. So when the cells become black, it means that they're placing phone calls, these signals that are sending you. And in saying years, there are neighborhoods, nerve cells, all placing phone calls together. And this is part of another principle of development, and the cells that fire together wire together. So this is a way that the eye can sort of test that this connection is orderly and the target structure is wrong. So this is really jump-starting the visions as possible in guttural and rather than the cone appear. And now we know that this happens in the visual system. It's been found that this kind of jump-starting and testing is happening all over the brain throughout the development very early on. And you're studying ways to potentially reopen the visual system. Tell us about all about it. So the question really is, if these windows are closed, can you open the doors up at any time? You're trying to understand how to do that. It's really important to know about the molecular structure, about what are the molecules that are opening and closing these developmental closing periods. And in particular, what is the molecular system that controls the pruning process itself? This selection system we should keep. How does the brain know that certain synapses get used and other synapses have not been used so much? So we don't need them. We actually need to, and these animal models that are beginning to discover these molecules and pruning them, and doing that, in fact, find another candidate molecules that we want to test to see if they're important for this pruning process. So we genetically edited molecules in mice to see what kind of critical periods in this pruning to our surprise and delight, we discovered that certainties in these molecular structures were not there, permitting the network and the persistence of the developmental critical period and to sit. And in fact, it fails to happen again and again. So this is illustrating 2 points. 1, it is possible to continue, to extend the critical period for a longer period of time. And it also indicates that the idea that there are multiple ways to go through this regulation in a deliberate way is only known as a whole story and a molecular braille. As an adult, I learned French with an accent. And for example, that's an interesting point. Alfred smiling and shaking his head as a neurologist. And what you want to take out of is, as a critical, clinical neurologist who thinks about this, there's a balance between the stability and the plasticity with patients with strokes. And what do you think about NIM in kids? And everybody's obviously going to sound legit. We got to figure out ways to understand these windows in kids for diseased adults and concepts of the wise man in the topics that are dubbed as double-edged swords. Having a great, efficient plastic brain that is able to get us from point A to B, and we're learning French and English without an accent, and it makes it really appealing to have too much of this plasticity that comes with a cost. If you don't have a genetically engineered mouse, baby by design, this pathology, then brains are not too plastic, and they're learning too fast at face value. It looks like a great thing. The fire above the average going in front of us, opening up the boxes of matches, and they're burning the ground down and telling us that it's wrong to learn in this way. Through these phones and numbers and phone numbers, I said, it's sort of cool to insert as jokes. It comes at a cost. What happens to the brain is it normally yields to influence to the environmental change. And then we stop, and then we experience a new thing, and then you think false. Or falsities. And you discover this new thing that doesn't get colored in. That you just learned, or you just colored in, is the change. And then the chain, it's followed to the